And welcome, Jessica of Ladyada.
We glow.
Carousel. Where is Sanctuary, Ladyada?
I'm not even a big Logan to Run fan.
Yeah?
Yeah. I've never even watched the whole thing through.
Yeah.
You know. Here you go. It's for you.
Thanks. I'm going to renew.
Renew.
Actually, I'm going to run.
You're going to go run.
Yeah. Okay.
Okay, so here we are at my desk, not running away. I'm over 30, but it's going to be okay. Tonight I thought I would do kind of like a upkeep, redo, check-in on the Circuit Playground Express IR receive and transmit code. I was like noodling around with it last night, like 2 a.m. And I actually had a little bit more time today to try out some different libraries, so I thought it would be fun to talk about. But I thought first I would talk about like how IR works, because maybe some people watching don't know how IR works. I thought that would be pretty handy.
Okay, let's do this.
You want to do that?
Yeah.
So the basics behind IR is, it's infrared. That's what IR stands for. And it's a bigger waveform than red. So it's like right below what humans can see. And this is kind of neat because it means that you can use it to like illuminate night vision. So like IR is used for night vision. You can use it for transmitting data using IR remotes. You can also use it for digital whiteboards. If you're a digital whiteboard, it probably uses IR. I think even the Kinect used IR grids. Basically it's a way to like have light that a computer can see very easily, but that humans can't see very easily. So the really neat thing is it's just a little bit lower on the spectrum than red, and so we can't see it, but computers can see it just fine. So can cameras, especially if they don't have an IR filter on. Sometimes they do remove the IR filter so they don't get that noise. And so IR is really popular for use because, like I mentioned last night, it has a lot of the benefits of wireless communication. Wires, you can transmit data here and there, but it doesn't use the low enough frequencies that would need to be like FCC regulated or deal with antennas. It's basically you're just transmitting photons, and because you're transmitting photons, you can do it very easily. The power requirements are pretty low. It's really easy to do. You don't have to worry about antenna tuning or anything. You just have an IR transmitter and IR receiver. So other than that, it's kind of similar to wireless, except you don't have a bidirectional communication. It's like you have to have one transmit LED and one receive LED basically for each set rather than like trying to multiplex an antenna. But other than that, it's very similar to wireless. You'll have protocols and layers of filtration and error correction on top of it because like all wireless protocols, IR is, it's not perfect. Like light can affect it if you're not line of sight. Sometimes the IR doesn't bounce very nicely off of walls, so you're not going to get a very good signal. You can have really, really bright LEDs and do IR transmission from like, half a mile away, but it is tougher than, at that range, you probably want to use something like a wireless transmission, like 400 megahertz or 900 megahertz. But we like the terahertz range a little bit. So one thing that's interesting about IR is, another thing that's cool about IR, it's really cheap. Compared to a wireless radio, which is at least a couple bucks, and needs all these tuned components, IR transmitter LEDs are like 5 cents. You can get them in bulk for 5 cents or less. And then IR receivers are also really inexpensive. They're like 50 cents, 20 cents in bulk. So it's a really easy way to do transmission. Also, almost everybody has a transmitter at home. Like here's my TV remote. And you can see the IR LED over here. Let's see if this camera has a filter. So it does. So it's not.
Yeah, you can see it.
Barely see it. The overhead, though, is really good. Do you want to go to the overhead? 'Cause the overhead is way better at seeing IR. Get out of the way. So that you can really see it. But like human vision, you can't see it, but as you can tell, the computer vision can see it really well. So almost everybody has remote controls. I think, what's the question?
Question is, what frequencies do TV remotes and such use?
Well, there's 2 frequencies. There's actually 3 frequencies involved. First is the frequency of the LED, right? Because it is, usually talk about it in nanometers, the inverse of the frequency. But what really is going on is that this is an LED with a certain frequency, which is very, very high. And so it's near the visible range. And often these are referred to in terms of nanometers. So this is a usually 940 nanometer LED. That's an IR LED, but that's not always true. It can vary. Thinking sometimes it's a little bit lower, a little bit less, but almost always 940 nanometers. Write that down because it's a pretty handy. I was going to mention it anyways. So you have the IR LED, which is about 940 nanometers. Bam! So the transmitter LED is running at 940, and then there's the receiver, which is actually essentially also an LED. It's just an LED with a really big surface area, and this is also tuned to 940 nanometers, so that this one will receive the signal. And so when you look at, for example, we have the IR receiver and transmitter LED on the circuit playground, and I can show that. They're really both just LEDs, just one is like a little, this one's black. It just has a filter on it. Sorry. This one's black. That's the receiver LED, and that's a transmitter LED. Remember, like IR light receiving and transmitting, it's the same PN diode. It's just, so they're slightly built a little bit differently. Like this would be a very bad receiver. This would be a very, very bad transmitter because it's got a filter on it. But they're pretty much just LEDs, and they're just tuned to that 940 nanometers. And so what you can do if you don't want to use an IR protocol is you can actually just like turn this LED on and receive the signal on the other side. Just like literally you turn the LED on and then you look to see if this LED receives the signal. And actually we have those in the shop. They're called IR brake beams. Can you go to the compy? I'll show this. So we have, wait, hold on, let me shrink this a little bit. Okay, so these are called IR brake beam sensors, and we have 2 of them in the shop. We have one that's 3 millimeters, and we have one that's 5 millimeters. And if you look at this carefully, you'll see like over here, this is the receiver, and again, it's just a black LED. It's actually a photo transistor, so it's got some gain to it. you power it and it gives you a signal, so you have because the signal otherwise is very, very weak. And then on the other side, you have the transmitter, and it's got a clear LED. So the same thing, really. You have two LEDs and they're matched up. Now you can modulate them, but people tend not to actually, because they're just usually like, this far apart. You have the LED light up, and then what happens is the receiver on the other side is receiving it, right, just like this. And when you put your hand in the middle, you block the light, and this signal basically says, hey, something is blocking it to break beam. The beam has broken. And this is actually almost identical to another kind of sensor. So the IR, engineers love IR. Engineers are like, if they can use IR for something, they'll use it. This is also used for proximity sensing. So if you look at, for example, the VCNL 4010, if you look inside the data sheet, you'd find out that this sensor is also just an IR LED and an IR receiver. They're just next to each other. So instead of like this, they're actually like, there's like kind of like a little wall type thing. And then I'll make this dark so this is the receiver. So this is transmitting, and then when you put your hand in front, this light bounces off of your hand and back to the receiver, unless you've detected proximity. So these are used for like measuring, when you go to the restroom and you wave your hand in front of something. That's what it's doing. It's the opposite of a break beam, right? It's detecting when something is reflecting the light back onto the sensor. So this is also IR. Really handy. Isn't IR great? IR is just used for everything. So these are just plain IR LEDs and receivers. Again, super inexpensive. Like you can get this jig together yourself for like 10 cents. What a good deal in production. And this is good enough for proximity detection. And there's probably some other uses I can't think of. But this isn't great for transmitting data because, well, if you want to transmit data, right, you have to send like 10, 10, 111100, right? You have to send like bits to make bytes. So when you do that, you actually don't, what you would think you would do is actually just like, okay, we'll turn the LED like on and then off and then on and then off and then on again to send 10101. But actually that's not what happens because, for one, if you really want to turn these LEDs on really bright, you have to pulse them. You want the amount of time they're on to be very, very short. That's one reason. And the second reason is that when you're just detecting if light is there or not, and you're like only 4 inches away, like all these proximity sensors, these break beams, they only really work up to like 6, maybe 12 inches away. They're not really meant for long distance. Once you want to do a long distance data transmission, you have to have some error correction, some way to filter it, some way to make sure that you don't have ambient noise in the way. Because right now, even though we can't see IR, there's IR all over the place coming from the LEDs, fluorescent lights, incandescent lights. They all emit IR, and so you can't just have the LED on or off. What's up?
Well, sometimes I have questions. Or
Yeah, ask questions.
That was pretty abrupt. You told me about was it your advisor or someone in IT had this thing where you could broadcast data from the IR.
That was my roommate.
Oh.
And yeah, he has a company called Pixmob. And what they do is they have really, 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 really big IR transmitters. Like they're like 1 or 2 foot around, and they're made out of thousands of LEDs. And what he does is when you go to like the Super Bowl and you see that they have like everyone has these little like light things, and the lights change, like, and they draw patterns. The way that works is actually IR transmission. By beaming IR data, all the little receivers know where they are because like they're being hit with the beam, and there's like multiple beams, and so they can draw onto the crowd basically using IR beams. And like it's one of those things where a lot of people have tried to do it with radio, but it's just so hard. like one of the nice things about IR is you can really have it be very directional, because you can put a lens on the LED and make it be only like 5 degrees of spread, and then you can have cones, and you can have like coverings to make sure the LED is really pinpointed. It's very hard to do that with radio. Like radio, you can make it directional, but it's hard to make it as directional as light. So with the light beams, he can paint on the crowds. Check it; it's called Pixmob, like Pixmob, and you see them. I know that he's done a bunch of concerts and Super Bowl type events. Do you have any other questions?
No.
Okay.
I just people like that.
That's cool. I'm glad. So back to this. So you can't just send on and off. You can't turn the LED on and off because it's actually really hard for the receiver to know when the LED is on and off depending on how bright it is in the room. So what they do is they actually modulate the signal. So not only do you have this 940 nanometer LED, but the signal that's sent, when you want to send a 1, you actually turn the LED on or off really, really fast, like very, very fast, multiple times. And then when you don't send the modulated signal, that's 0. So this is 1, 0, 1. This is called a mark, and this is called a space. So when you are sending a mark, that is turning the LED on at 38 kilohertz, approximately. So it's turning on and on really, really fast, 38 kilohertz, and then it's on and off for like, a couple of microseconds at a time, usually like 500 microseconds or something. So this is, 100 plus microseconds per, on and off, and then it's it's turning on and off very fast for it to be considered a 1 signal, and it's completely quiet for 0 signals, and you alternate these, sending modulated signal, not sending modulated signal. So you have the 940 nanometers for the LED. You got the frequency of the modulation when you are sending signal, and that varies. It can actually vary from like 24 kilohertz, I think, or 20 kilohertz I once saw, up to, I think, 50 kilohertz. But like almost everybody nowadays uses 38. It's almost standardized. Why? I don't know. I actually don't know exactly why they picked 38 kilohertz, but it's a good frequency because it's pretty high up. It's definitely way higher than the 60 hertz or 120 hertz that you're going to get from fluorescent lights, and maybe they just wanted to make it higher enough that you wouldn't get any of the fluorescent light, not resonance, the whatever, I forgot the word off the top of my head. What's up?
I remember when the Palm Pilots came out.
Yeah.
And the watches, and you would program it using an IR transmitter and receiver.
Yes.
That was kind of cool.
So yeah, once you're sending like 1s and 0s, so this is a way to just send like really basic data. But then on top of this, you can have other protocols like IRDA. So on top of this, there's other protocols. So this is like its own protocol, and then there's like you can send data on and off, and then the width of these spaces is another frequency component. And then you can have a protocol on top of that, like IRDA, which is like a data transmission, receive and transmit system. I don't know why Palm Pilot didn't use RF, but maybe another thing, it's like maybe it was just cheaper and easier. Radios, at the time when the Palm Pilot came out, I think we were barely just getting to the point of having low-cost 2.4 gigahertz radios. It was very, very new at the time. Was there Wi-Fi when Palm Pilots came out?
No.
It was just
in fact,
started.
Yeah, in fact, I remember because in my previous life, I worked on OmniSky, which was a modem for the Palm Pilot, and it used the cell networks. There wasn't widespread Wi-Fi quite yet.
Yes, that's right.
Super weird.
We were still using Ethernet at the time. There was no such thing as Wi-Fi. Some people had 802.11b, but it was like, or 811a, but really sucked. Sorry, the word was harmonics. So they wanted to make 38 kilohertz high enough that maybe it would be affected by harmonics from fluorescent lights and just stuff around the house. And so when you get the signal, when you're building a receiver, You have to have a couple things going. Again, you have to have a tuned receiver for the frequency of the LED that you're using, probably around 940 nanometers. And then you also want to do a filtration on top of that that does a 38 kilohertz, it looks for the 38 kilohertz signal and takes that out for you and just gives you the envelope. And so the chip I'm using is, well, in the store we have one called the TSOP 38238. Oh, can you go to the copy? I'll show this. I'll figure out how to. I've the wrong direction. Well, you know what? I have this here. That's a little better. Okay, so this is the TSOP 38238. And seeing these 38s pretty much tells you it's a 38 kilohertz sensor. So it's tuned to that frequency. Again, you can get ones tuned to other frequency. And then if you look at the data sheet, they're like so easy. And what's nice about these chips, they're chips inside, is they do a ton of filtering for you. So you only have to give it power, ground, and then output pin. That's it. You can even power them from 2 to 5 volts. They're just like so generic. They're used in almost everything. And you can get these for maybe, you know, $1 or $2. And then if you're buying them in bulk, you get them for a lot less. And inside, here's what's going on. So you've got that diode. It's called a pin diode. I don't know exactly what pin stands for. I mean, maybe it's like something, maybe there's something next to the P and N layer. It's a pin. Anyways, this is a receiver LED. So it looks like a diode, but it's, you know, light comes in, and then it goes into an automatic gain control. So, you know, based on how much ambient light there is and how good the signal is, it will actually do a bunch of amplification, filtering, amplification in a cycle, in a feedback loop, and then this bandpass is looking for the 38 kilohertz, and then what it does is it demodulates it. It takes out that 38 kilohertz, so that the signal you get doesn't have that 38 kilohertz component. It looks like on off, just like really nice. And then the output just comes out to a transistor output, which is all good. And that's pretty much it. So the only difference, and they even tell you here, you know, what it's looking for. And there's a lot of optimizations, for example. One thing to watch for is the burst length matters. So it will actually filter out signals if the bursts, those 38 kilohertz pulses.
Pen equals P region, I region, N region.
Yeah, what's the I? Like,
Yeah, hey Terry, what does the I stand for?
yeah. Like
P region, I region, N region. PIN, P-I-N.
I know, yes. There's like the P and the N, and then there's something in the middle.
P to the I to the N.
I don't know. So you have to watch out for is these sensors are quite smart, and they look for the pulse widths.
Intrinsic. Ron says it's intrinsic.
All right, great. It's an intrinsic layer. I don't know. Probably just a layer that makes it very sensitive. You know, it's very sensitive to light, and it's exposed. I don't know exactly what.
There's all sorts of learning going on.
Yeah, I'm not sure exactly. I never studied pin diodes. So when you are looking for these, they do come in multiple flavors. And not only do you want to look for, you know, the frequency, 940 nanometers, the frequency of the modulation, 38 kilohertz, but you also have to look at the burst lengths. And when you are looking at it, it will tell you which version you want. So for example, there is the TSOP 38.2, 39.2 is 3.9 kilohertz and 3.8 kilohertz. And then there's the 38.4 and 39.4. And what it matters is
Undoped intrinsic semiconductor.
oh,
That's cool.
what really matters is how many bursts it can handle, because some remotes have like these really, really long data strings, and some of them have really short ones. And so you want to make sure that if you're using it with a remote that pretty much, if you're pairing this with a device that's going to be used with a remote that has really long codes, you want to get a long code receiver. And if you're getting one that uses short codes, you want to get a short code receiver because it'll try to do some smart filtering to make sure that you don't get codes that are too short or too long, or it'll start cutting off. So what you look for is, what you want to look for is over here, it'll say, which codes you're using. So for example, NEC codes. Well, they're all pretty good for NEC codes, but like are you using Sony codes? Sony codes I think are really long. Yeah, they're 70 cycles, so you want to make sure that you're using the 38.2 for long cycles. And then, but so you're wondering why not just always use the ones that can handle the longest bursts? Like this one, the 38.2 can handle NEC, RC5, RC6, Sony, Thomson, Mitsubishi, and Sharp. So you're like, well, why even use the 38.4 over here, which can only do NEC, RC4, RC5, Thomson, and Sharp? Well, the answer is not a lot of people use Sony remotes. Like even this Panasonic remote, this Toshiba remote, it uses NEC codes. And all these little remotes that you see all around everywhere with like devices, they're all NEC too. Almost everybody uses the NEC code base. I don't know why. Maybe it's just the easiest to program. Maybe like some Chinese developer released a library, and so.
Are you going to be on this for a couple minutes?
Yeah, sure.
Okay, I'll be right back.
Okay. So when you're picking the receiver, if you're going to be using NEC remotes, which like you probably are, grab the 38.4 because it'll be less flaky. I think the receivers that I've got for the Circuit Playground, I just picked the 38.2s because I wasn't sure which one I was going to use. And it turns out, especially when there's a lot of lights on in the room, and I've got, we have these Philips Hue lights, and so they do a lot of PWMing, and so there's a lot of noise coming in that way. And, we have these lights here, and you have some fluorescence. All this noise builds up, and so you want to basically get the 38.4 series or the short code series if you're using short code remotes. So the good news is these work great. The bad news is that all of these receivers are almost always through hole. It's actually really, really hard to find a surface mount version of these sensors. But when I was looking at Parallax, they had this badge. It's one of the things I was looking at when I was looking at Circuit Playground. Let's see if I can find this badge. Yeah. In the badge, they have an IR receiver. Yeah, infrared communication. And I was like, oh, that's neat, because it was like all surface mount. And then when I looked, I saw that they had a surface mount receiver. So if you go to DigiKey and say infrared receiver. Welcome back. And they're actually just called remote receivers.
I had to see a man about a mule.
Yeah. So you can pick out remote receivers, and they they come in like all sorts of shapes and sizes and versions. There are surface mount ones, but they're a little pricey in my opinion. So let's filter. Well, let's look for active ones.
Oh, someone had a question. How did the watches work that were programmed from a CRT display? From what I recall, they flashed.
I think there's actually they didn't use infrared. They just used light.
Yeah, they just flashed on the screen, like really fast.
We had a kit from someone who used that technique. Actually, you know who used that technique was the Scheme wearable kids.
Oh yeah.
Oh my god, my memory's so going. I cannot remember what's the name of the.
We'll find out later.
They're not around anymore.
Yeah.
Okay, so these are some surface mount ones. Ooh, I love that image over. So you can see in the center there, that's that IR LED, and then there's a chip around it. It's a surface mount part. This one has a nice dual lens, and then of course pads. What's neat about this design actually is you can mount it facing up, or you can get it rotated so you can have it be right angle as well. And then this one's kind of neat too. This is unfortunately not a great view of it, but the LED's on the other side. Let's see, maybe I can look at the data sheet. Yeah, on the other side of the component, there's a window. So this is a very, very small IR receiver. which is kind of neat, completely integrated. You can see Vishay like kind of has this market down. They got the TSOP series down. So, but it's almost the same. So basically, they have like one really great chip design. They just kind of redo it over and over again. But they're all a little pricey. So, 79 cents, which isn't bad, but it does add a lot of cost to Circuit Playground. So when you sort by price, you'll see that they do have a series that's just the conditioning, and it's they're pretty cheap. They're only 25 cents or so when you get a bunch of them at a time. And then of course you can go to Vishay and like be like, hey, I want better pricing. I think I got them down to 20 cents in the end by telling them that it was for the children. And this part is just the processing chip. It doesn't include the LED. The LED you have to get separate. But you can see the pricing is a lot better. So like, even though this doesn't include the LED, it's like 25 cents. The next best one that does include an LED is 65 cents. There's a couple of like these, Everlight has a couple of modules, but nobody has them in stock, so I kind of got spooked from using them. But as you can see, they're almost all 38 kilohertz. This one's 36 kilohertz. So you can see there's a little bit of variation, 36, and this one's maybe 38. They all run from 2 to 5 volts, which is lovely. And then when you look at this data sheet, it's just a chip. And, it's intelligent AGC, so that's the stuff that you have to watch out for to make sure you get the correct code width. And then all you do is you add in resistor capacitor for just some basic power filtering over here, and then an LED. And so the next thing you have to do is just pick up an LED. So then if you look for pin diode, don't forget the intrinsic. Can I have a drink? Yes. Okay, so we want to get like a photodiode. Thank you. Whoa, 68,000 different diodes. Okay, so now you want to get a diode, so you can check the wavelength. Whoa, hold on. Browser's acting funky. So you can actually look for different colors. We can also look at wavelengths. So this is, if you wanted to filter down, you can actually be off a little bit, by the way. If you're like, oh, I found a really nice diode, but it's like 930 or 950, it's okay. There's a little bit of spread anyways. But let's pick up an infrared one. And then, ooh, my browser's really being sluggish. And then sort by price. And then you can see some nice pin diodes here. This is the one I ended up using, the PD15 from Everlight. And you can see it's 8 cents. So even though you're getting two components, there's the 8 cent LED and then like the 25 cent receiver, it's still half the cost of getting an integrated solution. So if you can get away with it, two different parts is good. What's up?
You're at the 30-minute mark.
Well, I think that's actually a pretty good intro. I mean, we could stop now and then.
Yeah. Let's wrap up and then we'll keep doing this during the week.
Okay. Well, that's the receiver. So maybe I'll just show it running on the Circuit Playground. Do you want to just go to the overhead and I'll show it off? We can always do more streams in the week.
Yeah.
Okay, so let's go to overhead. Actually, let me go with this one. This one's right. So this is. Hold on. Okay, so, I've got my tweezers. Oh, I've got my So over here is the pin diode. It's very small. Hold on. Okay. So over here you can see that black pin diode. And then the receiver chip is actually over here. And then the capacitor and the resistor that they recommend is right next to it. So what actually is nice is, even though this is also a little bit bigger than integrated solution, well, it's about the same size as integrated solution, like an all-in-one, but I could spread it out. So I could put the receiver LED over here and then the chip down here. So they're close to each other. They're very close, but just far enough away that that I could kind of like use that space intelligently. And then over on the software side, I have tried 2 libraries. There's IRlib2, which is Chris Young's, and that works. And I also am trying out IR Remote, which is Ken Sheriff's library. It's pretty popular, people use it, so I thought like, well, I want to make sure that it works with this as well. So then let's go to the Compy. And I just have a really basic demo where the receiver pin is number 39, just turned out what it is. And then I turn on LED, and then I turn on the IR, but I also have the strip of NeoPixels, the LEDs around the circuit playground. And then I'm going to be looking for 2 codes, and depending on the code, I'll change the NeoPixel color. So it's a really good way to tell if I'm receiving different codes. So it also will print out what code I did get, because you can try the remote and see what code it's transmitting. So let's upload this to my circuit playground. And I thought we could probe the pin diodes too and see what that looks like. Okay, so it's going to take us a minute to compile. Any questions while I wait?
No.
Comments? Diode explanations? What's fun is then we can make a TV gone in a future episode. Compile, compile, compile. Compile, compile, compile. Alright. So let's try this out. So I've got my remote control, my little happy friendly remote. So let's try this. So you can see it's printing out the different codes. So this is the volume down code, and then when I press red, it's the volume up code. So these are the 2 codes you get, FD00FF, FD40BF. Even though these are 32-bit, you only really get 24 bits. I don't know, I guess they just use the rest of them. Or they're zeroed out. And then if you repeat a code, so if you hold down a button, you'll get FFFF. That's the repeat code. That just lets you know like the button was held down, and then you don't get a button up. Instead, you just don't get any more signals. So that's kind of neat. Seems like it's receiving the codes just fine. And then if you go to the overhead, and I've got my remote here, hold on. As I point and press my button, I just have to aim it. I can change the color of the LED. Nice demo. And so,
Good work.
is there a question, or should I
No.
try another thing? Well, let me do one last thing, because I thought it'd be kind of fun. I will clip on, and then can you go to the overhead real fast?
We are on the overhead.
Oh, sorry. Yeah, you're right. Good work, Bill.
Yeah.
Let's probe not the this pin, but the other side of the pin diodes. This is the signal side. So we're probing this, and then let's go to the scope cam. Let's just see what comes up. Let's move this down. One moment. Scope adjustment. Yeah, maybe. That's good. Okay, so that's it's kind of hovering at about let's see, measure. What about 1.5 volts? So let's send a signal and see what happens. Oh, you can barely see it. Hold on, I think I do see it. Let me AC couple in. Let's go up to like 10 millivolts, 50 millivolts. Okay, so now we're seeing the AC signal. Let's try sending this again. Oh, you can see it a little bit. Hold on. Yeah, if I'm really close, you can start seeing the signal. But what's interesting is like, okay, so like if I hold the IR remote with like holding down the button and I'm like 3 inches away, you can actually pretty much see the signal quite nicely. So let me, hold on. Okay, so you can see the signal pretty nicely. But what's interesting is that once I get, even like 2 feet away, you can barely see the signal out of the pin diode. This just shows the quality of the filtering and automatic gain control that's going on inside of the receiver chip. It's kind of neat. Hold on, let me bring down the trigger. Yeah, it's amazing. Like I can barely see it on the oscilloscope, but signals are coming in on the serial console. So the upshot is, if you want to try to do this on your own with just like a pin diode and an op amp, you could probably kind of get something working from a couple inches away. But if you want to really have your remote work from up to 15 feet away, you need to get one of these receiver chips. Like they do the job really, really well. It's worth the 20 cents. I kind of like tried a little bit to like dink around and get something working with a basic op amp, and I couldn't get anything working nearly as well as these. So I ended up just saying like, you know what, it's worth it. Just get that extra chip, and then you pass your filter into it, and then it just sends you the signal out so nice and clean. It's a joy. It was really easy to get it working with the IR remote library too. So, yay! IR receiving.
Okay.
Change the LED color.
That's your desk of Ladyada.
Red, blue, red, blue, red, blue, red, blue, red, blue, red,
Okay.
blue, red.
All right, we're here all week. Join us on Wednesday, 7:30 p.m. Show and Tell. Ask an Engineer, 8 p.m. Eastern Time. I'm doing this every week. Support Adafruit.com, buy a kit, and more. This was Desk of Ladyada. Thank you, Ladyada.
Yay! Next time we'll do IR transmit.
Yeah. All right, say goodbye.
Goodbye. Red, blue, red, blue.